way correctly, and as you were leaving, I was trying to draw a hexagon, which I could not draw, as you can see. All right?
The video just ended there.
Yeah, well, I was trying to draw this, which is benzene, to show that these double bonds can go anywhere on this ring. And you draw it as a circle to show that those double bonds can move. So, because there is resonance, we have to sometimes figure out what the formal charge is of a compound or an atom. So, formal charge, this is super important because you're going to have to do this on the AP test, I guarantee you. This is used to evaluate non-equivalent Lewis structures. Non-equivalent Lewis structures. So here's the goal. The goal when we're doing formal charge is two things. Thing number one is to have the lowest possible /0, right? The lowest possible /0 formal charge overall. Formal charge overall. Am I on the screen? Yes. And also, any negative charge, if there is any negative formal charge, should be on the most electronegative atom. This is where I was getting confused in my head yesterday on a Monday. I kept talking about electronegativities, all right? And I was thinking of formal charge. So if there's a negative charge, it should be on the most electronegative atom. How do you calculate formal charge? I've done this different in years past. I'm going to do it some way new this year, all right? So I've never taught it like this, but I think it's going to make more sense. So formal charge is equal to the difference, all right? The difference between valence electrons and the electrons in atom ohms. And the difference, so it's the difference between valence electrons and the electrons in atom ohms. So put an asterisk by ohms. We know what an asterisk means now after yesterday, right? Yes?
Yes.
Yes. I'm just going to put it right here though. So when you're talking about owning, you only own half of each shared bond, I guess. So a bond represents 2 electrons, right? A dash is a bond, that's 2 electrons. If it's connected to something, that atom only owns half of that. Cool? I've done like equations in the past. I think this is going to be easier. So here we go. We're going to draw the following. We're going to draw POCl3. POCl3. We're going to Lewis structure for this. How many valence electrons does phosphorus have? 5. Oxygen has 6. Chlorine has
7
times 3,
21
for a total of
32.
32. So I have 32 valence electrons to show on here. Now, based off of yesterday, which one of these is going to go in the middle?
Carbon.
No, there's no carbon.
P.
Yeah, P. Why? Because P can have, if we need,
It holds more bonds.
yeah, it could also have an expanded octet, right? Yes? So if we needed it, we would want to have P in the middle. Yes?
Can you read the difference between that?
Difference between valence and electrons in atom ohms.
And
Difference between valence electrons and the electrons in atom ohms. And then my asterisk was only half of each shared bond is what is actually owned. So we're going to put P in the middle. So here's our P in the middle. We're going to attach everything else. So Cl, 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 O. And after you see it like this, we're thinking, is there going to be anything special about this Lewis structure? No, right? 32 divided by 4 is
8.
8. So all I have to do is just 3 lone pairs on everything, right? 3 lone pairs on everything, because that's going to give me 8 for each individual atom. So there's my Lewis structure for POCl3. So we're now going to calculate the formal charge of each individual atom. So I want to figure out the formal charge for phosphorus. So we're saying that it is the difference between valence electrons. How many valence electrons does phosphorus have on the periodic table? 5. And how many electrons does phosphorus own in this molecule?
Is that
4. Because it only owns half of each one of those bonds, right? So 5 minus 4 is 1. That's the formal charge for phosphorus. This is way easier than what I've done in the past. In the past, I've done valence electrons minus valence electrons, like 1/2 shared plus all lone pairs. This is way easier, okay? Way easier. So let's do it for oxygen. How many valence electrons does oxygen have? 6. How many does it own in this molecule? 7. It owns these lone pairs. It owns all of those individual electrons. 2, 4, 6 plus 1 is 7. 6 minus 7 is -1. -1. Try chlorine on your own. Formal charge of chlorine on your own. You guys got this. This is way better to teach it this way. I already have decided in my head. Valence electrons minus how many it owns.
But would it be CL3 or
We're just doing one individual chlorine. One individual chlorine. They're going to all be the same. All be the same. How many valence electrons does chlorine have? 7. How many does it own? 7, which equals 0. So the overall formal charge of this molecule is 0.
Dude, we're so good.
All right. So let's make a couple little stars down here. I'm going to move this up a little bit. So star number 1, the sum of the formal charges should equal the overall charge of the compound. The overall charge of the compound. So if you have something like NO3 minus 1, we know all of those individual atoms' formal charges are going to have to add up to -1. Star number 2. 2 bonded atoms can't have the same sign. So 2 bonded atoms can't have the same sign. So you'll never have a positive connected to a positive or negative connected to a negative. And lastly, this is the reason why we actually do this. This is the actual reason. If 2 or more, come on. Yo.
It's better than mine.
Hydro means there's no oxygen. It's hydronitric. It's all you just change the ending to ic.
It might just be
Because sulfic doesn't sound good. Sulfic doesn't sound like you're keeping the identity of the element. You want to keep the identity as close as you can. So you don't say phosphic, you say phosphoric. You don't say sulfic, you say sulfuric. But for nitrogen, you say nitric. No, it's just what sounds. You just have to kind of know that. All right, yep. Moving on. If two or more Lewis structures exist, that means there's what? Resonance. Yep. That means there's resonance. You're going to choose the one with the lowest formal charge. With the lowest formal charge. That was really bad handwriting. But that says, if 2 or more Lewis structures exist, there's resonance. Choose the one with the lowest formal charge. So, let's look at CO2, carbon dioxide. Carbon dioxide. There's actually 2 Lewis structures you could draw for this correctly. Do it. So draw the 2 possible Lewis structures for carbon dioxide. There's 2 that would both fulfill the octet rule. The Jackson 5. I think did we do this one yesterday?
Maybe.
Yeah.
I've got one where there's a double bond on both sides of carbon, right? What else could I do? I could do one with a single bonded oxygen on one side. I could do one with a triple bonded oxygen on the other side. Would that also work? It would work. But the formal charges tell the story. There was literally a question like this on the AP test 2 years ago. It gave you 2 molecules, and it said which molecule would exist, and you just had to look at the formal charge. So, this oxygen has how many valence electrons total? 6. How many does it own?
4.
2, 4, 5, 6, right? 6 minus 6 is? 0. So this one's going to be the same, also 0. Carbon has how many valence electrons? 4. How many does it own?
4.
All zeros. Over here, though, oxygen has 6. How many does it own?
5.
So this has a formal charge of
1.
positive 1. This carbon is still going to be 0. And this oxygen is going to have a formal charge of negative 1. So, do these both add up to 0? Yes. But which one has the most individual zeros in the compound? This one. That is what you do with formal charge. Got it? Pretty easy, right? Okay, we're ready to start VSEPR. Big day. Big day. I'm turning the page. Big day. So today we're talking about VSEPR, which is valence, shell, electron, pair, repulsion, and then theory. All right, it's not VSEPR. All right, it's just valence, shell, electron, pair, repulsion, and I put theory really small. All right. So, what do we do with VSEPR? We do a lot with VSEPR. We're going to be talking about shapes. We're going to be talking about polarities. We're going to be talking about angles. So much. We're going to be talking about hybridization. And we're going to be talking about bonding. So I got shapes, polarities, angles, hybridization, and bonding is what we can do with VSEPR. So we're going to start out with BeH2. So I have BeH2. BeH2. How many valence electrons does beryllium have? 2. Hydrogen has 1 times 2 is 2, for a total of how many valence electrons in this molecule? 4. So draw that Lewis structure. I've got BE attached to an H attached to another H. Blow up 2 balloons.
Does it matter what color?
Tie them off and tie them together. Blow up 2 balloons, tie them, and then also tie them together. Make them all equal size. Bigger than that. Bigger than that. Oh, shoot. All right, I'll take another one. Bigger. They want to be pretty big. Bigger.
So big.
Keep going.
A little bigger, Sean.
I'm getting there.
That's not, like that. That's too big.
Dude, it was all, I feel like it's gonna explode on there.
That's good. That's good. Brendan's size is good. That's good. But they need to be the same size.
We're supposed to tie them individually.
Tie them individually and then
Rick,
tie
I
them
can't
together.
This is too nuts. It's not stretchy.
Yes. Another partner. Open up your model kit. Open up your modeling kit. Build this molecule. All right.
Dude, I get to build a molecule.
I don't know if we have beryllium.
What color is beryllium?
We don't actually have it, so we'll choose something else. All right. What color can we use for that? Well, it matters. It does matter.
What is this? Dude, this is what I would look like if I
We're gonna tie them to each other. I don't know how, but we are.
This is what I would look like.
Use black for beryllium. Use black for beryllium. Use black for beryllium. Use black for beryllium. I said make them equal size. Wow. They're supposed to be.
Oh, he said this was good.
This one just has more shit.
No, he said it's Sean, that's good. He said that's too big. No, that's too good.
In theory, should we blow up another
No,
one?
he said.
No, he said ours was good.
He literally said. He said it's Sean, that's
No, I said that's too big.
and then it's good. After I made it less.
It's fine. It'll still work. Another partner, open up your laptop.
I'll do that. I'll let you guys do it. No, you guys have to do bonds. It's a very weak bonding.
And I want you to Google, let's see, what am I going to have you Google? Molecular shapes PHET. Molecular shapes PHET. P-H-E-T. Molecular shapes PHET.
Single covalent bonds as in water.
Did you guys build
Double as in
What?
Have you guys built
So this is a single
Use
bond.
the black.
Did you use the long ones or the short ones?
I heard it was a fit.
All right. You're Googling molecular shapes PHET. Then you're going to choose model when you get in there.
Oh, we did the gray one. Whoa.
All right.
Just use like.
So,
No.
molecular shapes PHET.
You literally have to.
Then you're choosing model. So start the PHET, and then choose model when you get in there. Okay.
Are we supposed to make one? How did you get that?
What?
Are we supposed to make beryllium?
How to use black? How to use a carbon? I think
Ours are
you can't. They should not be angled. So you have to choose
Wait.
something where they should be straight across.
No, it's
different black.
All right, because the electrons want to get as far away from each other as they possibly can.
too straight.
All right.
I don't know if we have the same black.
Yeah, ours
Yeah,
are
all
straight.
of ours yellow have straight across.
All right, then use yellow. The color's not important. Color's not important. So, let's talk about what we were talking about yesterday before we talk about all the shapes. So, first of all, here's my 2s electrons. Here's my 2p electrons. I have 2 in the 2s, and how many in my 2p?
2.
No, I have none. Right?
Zero.
These will be the outer electrons for beryllium. Agreed? Yes? How many hydrogens can I currently bond to beryllium? None. So what am I going to do with this electron? Promote it. I'm going to promote this electron to here. All right? Promote this electron to here. Now I have room for a hydrogen to come in here and bond, and a hydrogen to come in here and bond with my down. What would be my hybridization?
No clue. What does that word mean?
What word?
Hybridization.
Hybridization is what orbitals are hybridized. sp. This is sp hybridized because I have one s orbital and one p orbital hybridized. One s, one p.
So like
Yes.
if you filled up 2 of the P orbitals, would it be sp2?
It'd be sp2. Yes. Fill up all 3, it would be sp3. You got it. You got it. There's a shortcut, which I'll show you in a second. There is. Yes, there's actually an sp3d. There's an sp3d2. You got it. So, a couple other things. So what would this look like? It would look something like this. Here's my beryllium, if I was going to draw my orbitals. Remember how we do this yesterday? The little piece, then the big one, and then the little piece, and the big one, something like that, right?
I remember doing it, and I don't remember understanding it.
All right? This is what the sp orbitals look like, an sp hybridized orbital. The little balloon and the big balloon, right? Little balloon and the big balloon. Couple other minor things we've got to know is that a single bond is called a sigma bond. A single bond is a sigma bond. And to understand what a sigma bond is, we actually probably should define that. A sigma bond is end-to-end bonding of orbitals. End-to-end bonding of orbitals. End-to-end bonding of orbitals.
Yeah.
A sigma bond is different than a pi bond. All right? A pi bond is orbitals beside each other. So this is orbitals beside each other. So a single bond is a sigma bond. A pi bond is orbitals beside each other. So sigma bond, do you see how these are actually end to end? They're in a line.
Yes.
A pi bond, they'd be up like this beside each other.
Peace.
So this is a sigma bond. A pi bond, they'd be up like this beside each other. So end to end beside each other. I'm going to show you more of that later, probably tomorrow. Yes?
So you know how like the water, like when you draw it, it goes like that?
Yeah.
Is that what that is, or is that just a different
Water has
bond?
2 single bonds. All you have to know is a single bond is a sigma bond, and a double bond is a sigma and a pi. That's it. It's actually just counting up single or double bonds. But
And water bonds are next.
right, water bonds are single bonds, so they are sigma bonds. Because for a water bond, Jacob, you have 2 things connected in a line, and then 2 things connected in a line. There's 2 sigma bonds. 2 sigma bonds. So, bonds. We're almost ready to actually do this. Bonds hybridize to become equal energy. They want to become equal energy. Bonds hybridize to become equal energy. So, I can ask you a lot of things about this molecule. The first thing I could ask you would be, what is the electron pair structure? Short would be EPS. So, the electron pair structure, save a spot here, all right, is where are am I still on the screen? All right. Where are electrons paired? Where are electrons paired? Slash how many bonds plus lone pairs? Because the lone pairs really matter when we're talking about these shapes. So the electron pair structure is literally where are there electrons in the model? All right? This accounts for everything. So bonds and electrons. So if we're looking at our model here, what would be the shape of your electron pair structure of where there are electrons in what you just made right there, balloons and your molecule? I have an electron pair here, an electron pair here. They are in a line. So this is linear. Same with your balloons. Your balloons are in a line because the electrons want to get as far apart from each other as they can. They are linear. So my electron pair structure is linear. My electron pair structure is linear. We just said this, but hybridization for this, hybridization, I cannot talk, is SP. Now, my molecular structure is different than my electron pair structure. My molecular structure is where are actual atoms. So where are actual atoms? So my atoms are my hydrogen. Agreed? Yes?
Agreed.
So on this one, my molecular structure is actually the same as my electron pair structure. So because I have an atom here and an atom here, they are in a straight line. So my molecular structure is also linear. My molecular structure is also linear. Is this polar or nonpolar? Is this molecule polar or nonpolar? It's nonpolar. It's nonpolar. Is there any unequal distribution of charge on this molecule?
I don't know.
Could you cut it in half? You could, right?
With a sharp knife.
Yes, with a very sharp knife you can cut it in half. That's nonpolar. And then I could also talk about bonding if I wanted to. So if I asked you for bonding, how many single bonds are there? So how many sigma bonds are there? There's 2 sigma bonds. So that's like, is that the Greek for sigma? Does that look right? Something close to it? What angle are these bonds at?
180.
180. So there's a lot that you can do with this. Take a look at your FET. All right, take a look at your FET. This is pretty cool. So I'm going to flip over to HDMI for a second. This is what everybody has on their laptop. Switch. Do it. All right. So here we go. Here's my molecule. Check it out. I can click electron geometry.
What?
All right. It says it is linear. I can click molecular geometry. It's also linear. So this FET is also helpful. I'm trying to show you this in 3 different ways. Balloons, models, and the FET. For all of these. Because people learn different ways. All right? Just please don't go ahead on the FET. Okay? That's what I ask. Don't go ahead. Do you promise me? I'm looking at you guys. I'm looking at you guys. All right. So don't go ahead on the FET. I guess I can just leave this up like this. This will still work. Okay. So let me make this bigger. What'd you say? It is weird. Okay, so that's what we're going to be doing. So when I say VSEPR, you can tell me a lot of things about a molecule. Shall we try another one? Here we go. Let's do next BH3. 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 How many electrons in boron? 3. How many in hydrogen? 1 times 3 is? So a total of 6 electrons. So I'm going to do this one more time, maybe 2 more times. All right, I'm going to show the hybridization. 2s. Here's my 2p. I've got 1, 2 for boron, plus also I've got 1p, right? Yes?
Wait, why do you have this?
Because it has 3 valence electrons. So here's 1, 2. My third one would go in my 2p, right? How many hydrogens can currently bond with boron?
Just 1.
1. But how many do I want to bond?
3.
So I have to promote this up to here. And I'm going to now put a hydrogen here coming down, a hydrogen here coming down, and a hydrogen here coming down. So how many s orbitals did I hybridize?
1.
1. How many p orbitals did I hybridize?
2.
So my hybridization is
SP2.
sp2.
Wait, you hybridized 2 p orbitals?
I did.
How so?
Well, because these are as soon as I hybridize, they're all equal energy. So as soon as I promote one, everything is hybridized.
What does it mean for one to be hybridized?
Whenever I'm hybridizing, is if I'm moving anything from the s up to the p, they are now all equal energy. So they're hybridized. That's what that means.
You moved 1 from S to P though, right?
I moved 1 from s to p, but now these are all equal energy, all 3.
How are there 2 hybridized?
To what?
It says SP2.
Because I've got 2 hydrogens which are going to come down into my p's.
So is it when the hydrogens come down that it's hybridized?
Yeah, once you connect, it's officially hybridized. It's not really hybridized until you actually bond it. So yes. It's sp2. Your hybridization is basically saying how many electron sites do you have? I have 3 electron sites, so I have 1s and 2 p's. I have 1s and 2 p's. So where am I going to collect my things attaching from a hybridization?
So it doesn't necessarily have to do with the promoting. It's just like a different.
As soon as I promote it, it's hybridized. Something has to be promoted for it to be hybridized. So if nothing is promoted, it's just regular old orbitals,
So what's
right?
going from, what's being promoted?
This electron is being promoted to this p, leaving me 3 spots to bond hydrogen of equal energy once I do that.
Why does it fill out our arrows first? Like,
It-
the last one,
That's what I'd be doing.
This one this goes here, right?
yeah,
Then I'd fill this one down,
okay,
this one down, and this one down.
yeah.
Oh, wait a second. Did I draw that wrong?
Perhaps.
I didn't
that-
think you did, but maybe.
I don't think
It's got
maybe.
Jeez!
I was just putting it over there.
That was loud. That was really loud.
Well, now we can have 2 equal balloons.
Here's why. Here's why. That actually helped me think. Here's why it does not go here. Because boron is one of our exceptions to the rule. Because boron doesn't have to have a full octet, I'm going to fill it here first. Because boron does not have a full octet, I don't have to have this third one here. Because boron is one of the exceptions to the rules.
What does that have to do with anything?
Somebody asked why we didn't have to put, why did this third one not go over here? So I'm going to go here, here. Why didn't it go here?
Okay. So you're moving the 2.
I moved this one here. Yes.
So then where's the one, the hydrogen? Like,
Hydrogen 1,
yeah.
Oh,
hydrogen 2, right?
so you're making it a fake full. It's a fake full.
It's a fake full. Yeah.
It's
a fake full. All right, guys, do not get hung up on the hybridization. We got to keep going. We got to keep going. We got to keep going. Okay, let's draw this. Well, first of all, you need a third balloon. So blow up a third balloon and attach it.
Like the same size.
Same size. Yes.
Someone take this. I wouldn't know how to hide them.
What should we use for our... Do you have any reds?
Same size.
We do have red.
Do they have 3 holes?
They have 2 holes.
It's the same size.
We need 3 holes.
Blue.
Wait a minute, because you separate the atoms.
Blue is 4.
That's what happens when you separate the atoms.
4.
Wow.
Actually, just add 1 more to your black.
So light right now.
No, that's not going to work. Ah.
Yeah, purple has 3, but 1 glow.
And
Purple?
tie it together.
Yeah, purple's 3. Purple.
Yeah, but we got to make sure it actually looks right.
Am I tying this together?
Yes, tie them together.
It says 4. Wait.
I'm gonna pop up my nail.
Should have made these before you guys came in. What are you guys doing? Oh, do you guys have gray? Do you have gray? Use gray. Use gray. Just want to get these electrons as far apart from each other as possible. Ah! Got it? Yes, gray is what we want.
The gray only has
Oh, well, just look at
All
mine.
of that.
Just look at mine. Do you have your 3 balloons connected?
No.
So, Lewis dot structure, B, H, 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 because I want my electrons as far apart as possible. Far apart as possible. I could ask you, what is the electron pair structure So I have 3 pairs of electrons, right? Yes? 3 pairs of electrons. The 3 pairs of electrons, what shape would you say they are in? Trigonal, but also they're in one plane.
So a triangle.
Trigonal planar.
What the frick? Why can't you just say triangle?
Trigonal planar. All right? It's trigonal planar. Do you guys see it?
No.
You don't see it?
See the triangle?
It's a triangle. It's a triangle in a plane. Trigonal planar.
It's not like tall or.
Right. It's in one plane.
Yeah. Okay.
Trigonal planar. Trigonal planar. Hybridization, we already said, was sp2. Molecular structure. Where are my molecules? My molecules are located the same place as my electrons are, right? Yes? So it's also trigonal planar. Also trigonal planar. My angle. Where's my angle between my atoms?
30, 60.
120.
Wait, how are you figuring that out?
30, 60.
The angle between the 3, it's a complete
it's a
triangle,
circle.
right? It's a circle.
I forgot.
Split
about
into
that.
3, 120 degrees.
36
Between
degrees,
those,
I got there.
this is 120 degrees, right? That's 120.
Hey, technically it's a triangle.
The angle between your actual atoms. Your angle. All right? Your angle. Polar or non-polar?
That's
Non-polar.
This is
Non-polar.
non-polar.
Oh, yeah.
There's no uneven distribution of charge, right? There's no uneven distribution of charge. Agreed? So this is why I say it's not about splitting it in half. It's about an even distribution of charge.
When would there be an?
I'll show you. I'll show you. So that is BH3. Add another balloon. Add another balloon.
No way, we're running out of balloons.
All right, I'll get you another one. Now we're going to do NH3.
This is like me preparing for
NH3. By the way, if I go over to my FET, I'm going to add a bond. Check it out. Boom. I can show my bond angles. Boom. 120. So here it is on my FET.
Almost there.
All right. Added another one.
What are you doing? Show your bond angles.
You can click show bond angles. So add a 4th balloon. We're doing NH3. Nitrogen has how many valence electrons? 5. Hydrogen has 1 times 3, which is 3. 5 plus 3 is 8. So draw your Lewis structure. What's it going to look like? Nitrogen, hydrogen, 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 and I'm going to have what on this one? 1 what?
Lone pair.
This is what changes everything.
Are you?
The lone pair changes everything. Ooh, I like that you did blue for the lone pair. That's actually kind of cool. That's actually going to be helpful. All right? I should do that for everybody. The lone pair changes everything. All right? So, by the way, 2 bonding sites, right?
This is tragic.
2 bonding sites was what hybridization. That was just SP. SP. 3 bonding sites was SP2. Guess what 4 bonding sites is going to be? S1. There's 4 bonding sites here.
No.
I'm sorry, 4 electron sites. Sorry, 4 sites for electrons. There's only technically 3 bonding sites, but there's 4 electron sites here. Agreed? I have 1, 2, 3, 4 sites for electron pairs. Is there a pair here, 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 and here? There's 4 electron pairs. All right? So I could draw this, but I do not want to get hung up on this hybridization. All right? I don't want to get hung up on it.
From S to P. What happened to like 2S to P?
What? It's the outermost electrons. There's only going to be 1 S and 1 P in the outermost. Right? So, my electron pair structure. The electron pair structure. Where are the actual electron pairs located? You would agree that I have an electron pair here, 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 and here. They all count.
Yeah.
Yes? So my electron pair structure is what? What?
Trigonal something. Trigonal pyramidal.
Tetrahedral. Nice.
Yeah.
Tetrahedral.
Why isn't it
Tetrahedral is my electron pair structure.
Two-dimensional.
My hybridization, guys, the hybridization just has to add up to your electron pair sites. You know that you have one S, you have 3 possible P's, then you go into the D's. So how many electron pair sites do I have? 4 sites, right?
Yeah.
So SP3. One S counts as 1, right? So my hybridization is SP3. The molecular structure is different. It's now different because the molecular structure is only where the molecules are located. Look at their balloons. All right? Can you hold it from the balloon? Hold it from the balloon. Hold it from the blue balloon. Oh. All right? It would have been nice if it was tied together. All right, so here we go. This is important. All right? So it's only where the molecules are located. So, is this electron pair a molecule? No, it's not. All right? Can you tell that these are not in a plane anymore?
They're not.
So, take a look at my screen of what happens when I add a lone pair. Check it out. I'm going to put it at this angle. When I put a lone pair, it's going to do what? When I add a lone pair, it's going to repel. So I'm going to add a lone pair. It repels. So it repels. Yes. Pushes them away. So my molecular structure of where the molecules are is trigonal pyramidal, where the actual molecules
I think that
are.
was one thing.
All right? Where just the molecules are, it's trigonal pyramidal. Trigonal pyramidal. Trigonal pyramidal. Because it's a triangle in a pyramid.
Is this going to be on the
I
test?
really think
Yeah. All right? What? But they're not flat anymore. They went like this. They went from this is not the same as what you have there. They're actually in a triangle now. So the one balloon is the lone pair. So electron pair structure. Electron pair structure is every electron pair, including lone pairs. So as soon as you add lone pairs, that's when these are going to be different. Okay? As soon as lone pairs, these are not going to be the same anymore. That's the key. That's the key. So, polar or non-polar? Polar or non-polar? It's polar, right? Because I have an uneven distribution of charge here. Agreed? Yes. Definitely polar. Yes. What about the angle?
120.
109.5.
Oh, how did you know?
It says.
109.5. Whenever it is tetrahedral, it's 109.5. It's 109.5 whenever it's tetrahedral. Yeah. We'll talk more in a second. All right. Add another balloon. The next one we're making is PCl5. 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 I've got 5. 35. 5 plus 35 is 40. Now, are you guys able to think through this and think 40 electrons, right? 8 times 5 is 40. So is there going to be anything weird about this Lewis structure?
Shouldn't be.
No, it's just going to be 6, 6, 6, 6, 6 all the way around, right? Well, 6 electrons, 3 lone pairs. So this is going to be P, Cl, 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 Cl.
Wait, phosphorus has more than 6.
Yeah, the
Phosphorus an exception to that octet rule?
Yeah.
Suggestion. That's what that is.
Phosphorus can have an expanded. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's my Lewis structure.
6 times 5.
All right, I'm going to show you this one more time. The why behind this isn't super important. It's just understanding what the hybridization is. But here's the outermost electrons for phosphorus. This is not meant to confuse you. So here's my 3s. 3s for phosphorus. Yeah.
There is no D.
Yeah, there is. Just stay with me. So 3s is full. Agreed?
Yeah.
So I have 1, 2. 3s is full. How many of my 3p's are full for phosphorus?
3.
3. So up, up,
Why is it 3D?
up. Hold on. These are my 3p. And then these are going to be my
Don't step back.
D.
3ds, right? Think about it. After you do your 3p's, you go to 4s2 and then your 3ds. 3ds. What? Because 4s2 would not be, we have to go to the lowest energy level possible for hybridizing. If we're making these all equal energy, we have to go to the lowest energy level possible. So
P doesn't have D.
I'm going to promote this electron to here, right? I'm going to promote this electron to here, right? That gives me 5 bonding sites. Or you can just count how many things are connected. 1, 2, 3, 4, 5, right? So my hybridization is going to be sp3d.
Wait, why D?
Because I need one d. I need one hybridized d orbital to connect the last thing. All right? So hybridization,
Why is it 3?
sp3d.
Why is it like 3S instead of like 2S?
Huh?
Why is it like 3S, 3P, 3D instead of like
Because
2?
I'm just doing the outermost electrons.
I think that's enough. I mean, it's like
Phosphorus is 1s2, 2s2, 2p6, but the outermost are 3s2,
Oh.
3p.
I kind of understand that.
So all that matters for the hybridization, guys, is how many bonding sites? 5. What is 1s plus 3p's plus 1d? 5. All right? It just goes s, then the p's, then the d's, however many you need. You never go past sp3d2. In fact, I'm teaching you more than you need to know. The AP test, you never know you never even need to know past sp3. So I've already taken you further than you need to be. Already taken you further than you need to be. All right, here we go. Electron pair structure.
EPS.
What shape is that?
It's pentahedral.
Oh,
Pentahedral.
pentahedral.
Is it pentahedral?
How are they talking together?
This is your normal electron share.
Pentahedral.
Electrons.
Looks like a sword.
No, it's a flower.
Is this enough connected?
That's
Oh yeah, that's 5.
It's trigonal tetrahedral.
How many pyramids do you see?
2.
1.
2.
It's a little cold.
Trigonal bipyramidal.
Where's 2? Where's the 2?
Look, there's one here and there's one here.
Well, it depends on how you orient
Right?
it.
You have to know the shape.
It's like this
Yeah,
It's a
there's one up here and then there's one down here. It's trigonal bipyramidal. All right? Trigonal bipyramidal. Is there any lone pairs?
no.
No, so my molecular structure is also going to be
Wait, weren't there? There's like 6 on all the chlorines, right?
my tri by pi. No, I'm sorry, any lone pairs connected to the middle thing.
Oh,
Right.
okay.
So my MS is also tri by pi.
Wait, try what?
Tri by pi, same thing. Trigonal bipyramidal.
I
I just shortened it.
You got this here.
All right. What angles do I have? There's 2 different angles in this molecule.
109.5. 120.
120.
And 180.
No.
660.
90.
What? Oh.
I have 120 between the two, and then there's also 90.
Of course.
All right.
You know, of course.
If we go over to our molecule builder,
180. Yeah.
I'm going to delete this lone pair. Check it out. Add 1. Add 2. All right.
What?
You can kind of see, all right, the angles now. So I have a triangle coming up, and a triangle going down. It's 90 between these in the middle, but it's 120. Oh, I can touch that.
Why do I feel like there's 6 things there, and I only have 5?
There's 1, 2, wait a second. It's how many things are connected? There's 6 things, right? But how many things are connected? So these are all connected to phosphorus in the middle, right?
So like all the ties together would be the
Yes. Those are the nucleuses connected together. These are just these are like the electron clouds on the outside.
Okay.
So, all right. Try the 6th one really quick.
Ain't no way.
We don't have a 6th one.
Where is
Roll
it?
it up.
We don't
Try the 6th one really quick.
No, we have a 5th. No, we have a 5th. He's just a little small.
Try the 6th one really quick. Right?
I got the 5th.
We're not going to move on, but as people are doing this,
Wait,
here's my question for you.
molecules are dying.
All right. Who can visualize these shapes in their head fairly well?
No, not a couple people.
Who is like, heck no, ain't no way I can visualize these. So,
I'm like in the middle.
the second group has a lot to memorize. All right? The first group is going to be able to visualize them more. I am not a visualizer. I can understand this now because I've taught this for years. I can actually see it. When I learned this the first time, I was like, what the heck is going on?
It's so good.
Right?
Yeah.
So here we go. What shape would this be with 6?
Triangle.
A diamond.
So this is more based off of cube. This is more based off of how many faces there are on the outside.
I can't tell.
Hexahedral.
Octahedral.
Oh,
Don't worry about writing it down. We'll do this tomorrow. This is octahedral because there's 8 faces. I'm not making it up. There's 8 faces. We'll call it a day there. All right?
Wait, so Mr. Heller.
Yeah.
You just have to like, if you just memorize part of it, you know all the shapes.
Essentially.
What do we do with the